My today's topic is length contraction, which is an important topic in special theory relativity, which tells that if an object moves uh, close to the velocity of the light, then its length becomes shorter than the original length. Now we see from the figure that we have two frame of reference. One is the live frame, which is called the stationary frame, and the second is the moving frame. And the velocity of the moving frame and the object is the v. Now, before going into detail of the length contraction, we have to revise the Lorentz transformation, which relates the space-time coordinates of the moving frame and the lab frame. So we can see from the Lorentz transformation that f dash is equal to gamma x minus vt, where gamma is given by the equation 3, 1 upon square root of 1 minus v square upon c square. Now an object in the moving frame is AB. So if we measure the length of an object in the moving frame, that will be the xb dash minus xa dash, whereas the length of an object from the live frame will be xb minus xa. So from the Lorentz transformation equation 1, we have the coordinates of an object in the moving frame is xb dash is equal to gamma xb minus vt b, and xa will be gamma xa minus vt a. So the length of an object will be xb dash minus xa dash. That is called the proper length. Whereas xb minus xa, that is delta L, and that is called the relativistic length. So now subtracting this xb dash minus xa dash, we will get the proper length. So xb dash minus xa dash is equal to gamma xb minus xa minus v tb minus ta. Now since their tb and ta are the time coordinate in this frame, but since I have to measure the length of an object at the instant position time, so in this case we will have tb is equal to ta, so that term will be cancelled out. We will get the xp dash minus xa dash, that is delta L naught, is equal to gamma, and xb minus xa is the relativistic length, that is equal to delta A. Now substituting the value of gamma from this equation 3, we will get delta L is equal to delta L naught square root of 1 minus v square upon c square. So from this equation we can see that if an object is moving with velocity v, then its length appear to be the shorter. In equation 4, if we put the velocity of an object that is given by the v is the 0.1 times of the velocity of the light, then the length that we obtain approximately equal to the 0.995 of the proper length, or we can say that it is the 99.5% of the proper length, which is approximately equal to the original length. Now if we put the velocity of an object is equal to 0.8 c, then we will get delta L is equal to 0.6 of the proper length, or we can see that the 60% of the proper length, that is the 40% of the length will be shorter. Now if we put the v is equal to c, that the object is moving with the same velocity as the velocity of the light, then we will see that the delta L becomes 0, means the object will be disappeared. Okay, this variation will be more clear if we plot a graph between the ratio of velocity of an object to the velocity of an light and the ratio of the proper length to the relativistic length. So from the graph we can see if the object is at stationary position, that is the v is equal to 0, then this ratio will be equal to the 1. That is, the proper length and the relativistic length both will be same. But when the object starts moving and it approaches toward the velocity of the light, then the length contraction will be more, is visible. And when it reaches to the velocity of the light, then it approaches to the maximum contraction, and the delta L upon delta N upon delta L becomes 0 at the V is equal to C condition. Okay. So this is all about the length contraction. Thank you.